right, so let's take a look at these three. Hopefully you knew that one of them was going to be ipso substitution, one of them was going to be a benzyne intermediate, and the other one was going to be the Chichibabin reaction. And I actually even put them in the same order that I covered them, the ipso followed by the benzyne followed by the Chichibabin. So this one is the ipso substitution. You've got a strongly basic and nucleophilic reagent, the dimethyl amide ion. Come in here and push the pair of electrons out onto nitrogen where they're most stable. And then those electrons are going to flow back in to reestablish aromaticity and kick out the chloride leaving group. This compound that's the product of this reaction is actually called DMAP, dimethylaminopyridine, and it's a commonly used strong base. You'll probably see it, some of you, in your projects, used as a base. This lone pair is quite basic because of the ability to resonate the positive charge out onto that nitrogen when you use it. So it's often used as a enhancer of nucleophilic acyl substitution reactions, because it will actually react at this nitrogen with the carbonyl carbon to form a really reactive intermediate. It's a great leaving group. This one has the bromine in it. The phenol-lithium is actually to take that hydrogen off and form the benzyne intermediate, plus benzene. That's the other product. And then you've got a symmetrical intermediate that's going to be attacked by another molecule of the phenol-lithium to generate that lithium salt. In this case, there's no acid in the first step. It's an inert solvent. So that waits until the acid workup to get protonated. Use acid to form biphenyl. So the product is biphenyl. That's actually the side reaction that we saw in the first lab, where we did the Grignard reaction. We made bromobenzene into the Grignard and then treated that with the ketone, but there was some biphenyl in there because the phenyl magnesium bromide can react with extra bromide that's still around. This is why we made the Grignard reagent very slowly by adding the bromine just a little bit at a time. If you add the bromine all at once, then there's too much bromide around. Excuse me, and you can't suppress this side reaction. So that one was 3 steps. This one is 2 steps, so it's 4 points. This one was 3 steps, so it's 6 points. The other 10 points are here. This one is the Chichibabin reaction. So the NH2 minus can attack here, push a pair of electrons onto nitrogen. So similarly to the first reaction, the thing that allows this reaction to go is the ability of that nitrogen to stabilize that negative charge because of its electronegativity. This is then going to come back in and kick out hydride. To reestablish the aromatic ring. And then what causes this reaction to be favorable is the hydride taking off that hydrogen. form an anion that's resonance stabilized onto both nitrogens. And that anion then sits around until the acid workup. At which point it flux off one of those hydrogens to form the final product. Which is this one amino. Keep the double bonds in the right place. Isoquinoline. And it's almost always the position adjacent to the nitrogen in the ring, pyridine, quinoline, or isoquinoline, so that you can get this nice resonance stabilized anion where the lithium ion, or sodium ion in this case, I guess, is associated with both nitrogens at the same time. So that's 5 steps. Attack with the base, kick off hydride, and then some proton transfer reactions. I guess it's 4 steps, so it's 8 points. Pretty clear? One of each of the 3 types that are not electrophilic aromatic substitution. So hopefully that one went well.